Okay, good morning, everyone. And this is week number 9, water treatment with Mr. Mike Firlotte. And we should have another very interesting session looking at valves and pumps. So over to you, Mike.
All right, I'm just setting up the chat function for you guys. Give me 2 seconds here.
And in the chat function, Mike, we have corrected the situation we had of, so if you want to share any files, you can always do the attachment in there.
Okay.
Yeah, we got that sorted out.
I have 3 screens on here, so I lose where everybody is.
Okay.
So you guys are over here, and the presentation's over here, and the camera's on the last screen. So I don't seem to be looking at the camera. That's why I have you guys on one side and the camera on the other. So.
Okay, not a problem.
Okay. Well, good morning, everybody. It's lecture number 9, week 9. So it's good to see all the regulars back. I think, you know, we had a pretty good lecture for lecture 8 on the distribution. And this is just going to build a little bit on some of the parts and pieces that move water around the systems. And we're not only going to talk about the valves that we see at your booster station or your water treatment plant, but we also talk a little bit about the valves you'll see maybe in the roads, or, you know, and again, I have to speak more globally. People have different needs, especially when it comes to valves outside, just because of requirements. You know, correct me if I'm wrong for the people on the call here. How deep would you bury your valves? Like, I would imagine they would be quite shallow. So if you could put in the chat function, how deep approximately is your valves? I'm be curious to know. Some places in Canada here, we can't even bury anything just because of frost. And it just becomes impossible to break through that. Typically though, and say where I am here, everything's buried about 8 feet. So you can imagine that's a long way down to bury everything just to protect it from frost and weather conditions. So there's a bunch of different things that we'll be talking about throughout today. You guys can see my presentation okay? If you can give me a thumbs up, and just ensure that you guys can see the week 9 valves and pumps. Perfect, thank you. All right, and you guys know me by now. Again, been doing this a long time, and happy to be here to discuss a little bit more about valves and reservoirs. Right on. 4 feet, Shannon, thank you. That's about average, you know. In the southern climates, 4 feet is pretty average. You know, I've seen valves in some of the more northern communities here in Canada up to 12 feet down. Imagine to be safe with 12 feet down. That's a big hole when we actually have to go down and repair these things. So I got some pictures throughout the presentation here of some of my old crews actually out there installing pipes. Which is really interesting. Yeah, 4 feet's usually pretty standard, and when it comes to, say, regulations, 4 feet is usually at the point where you need to take extra precautions to make sure that you don't have a hole that collapses in. So we're going to talk about 2 main things: valves, pipes, and whatnot. And those are the big things that carry water from your plant through your system. What I want to talk about, especially when it comes to the test, there's a bunch of different valve types. So they'll ask you something like, which is the best valve to throttle or control flow, and which one's just used in on-off. And so we'll talk about those ones today, and a bunch of different pitfalls that I see out there that happens. So valves are used to isolate or control. That's the big thing. Yeah, either it's on off or it will control the flow in some way. Again, Lots of different valves out there, and let's just make sure we use the right valve for the right application. And that has to do with how they're designed on the inside. Also, things that people don't think about is that there is rubber or some sort of rubber part inside the valves. And for example, for you guys, if you use that valve on chlorinated water or chlorinated water design, then you better make sure that that internal design is ready to go for that. An example is I've seen valves that are for chlorinated water, and they're used and the rubber kind of swells out and then they don't close properly anymore. Or the disc on a butterfly valve is the wrong material and it prematurely corrodes, and so it doesn't seal anymore. And those are things we have to think about when we look at our valves, is making sure that what they call the seat is correct. And we'll take a look at that as we keep going. Talk about manual valves first, right? And that's the old type of valves that you guys as operators have to actually open it. And sometimes there's a wheel on the top or there's a handle on the top. And these are used in both your plants or in the distribution system. Sometimes you actually have to put a big curb key down there to operate these type of valves. And this is, hydrants are an example of that, or a curb stop that services your property, or a type of isolation valve that's in the road. These are all, you can't just push a button and these things open. You'll have to actually put some sort of key or some sort of wheel on it to open these valves, and that's manual. And here's an example of a manual valve here. Pretty typical. This is a butterfly style valve, and it's manual. Usually also called hand valve or a manually operated valve. Easily I could take this little handle off and I could put some sort of device on there that would open these valves, and we'll take a look at those in a second. This is pretty typical of what we see in a plant or a station and above ground. Underground though, this is pretty typical what we see underground. And this isn't a manual valve. And this particular one is just a curb stop, right? And this would provide service from your main to your dwelling. This is a great picture here. Let me just get my pen here. There's a bunch of cool words here we're going to keep kind of going over, right? A corporation stop. This is this piece right here, far left. And corporation stop, you can see the blue main. Corporation stop is what they call something that's right off the main. It's buried though. It is a valve, but the valve is buried. In order to get to this valve, I would have to open up the road here or open up the sidewalk and dig down to see the corporation stop. It is a buried valve. It's not accessible to be operated. It just turns on and off the service, and the white line is the service. The valve that can be used though, usually there's some sort of riser or some sort of pipe going to the surface, is going to be called a curb stop. And a lot of times, especially in Canada and the US, that the curb stop is actually the division line between property, this is usually the utility owner on this side of the curb stop, and this usually is the responsibility of the homeowner. And that's pretty typical. In this particular picture here, we also have a water meter. And inside your house, there's usually some sort of stop valve or a main shutoff inside the house. And I'll be telling you, a lot of the failures I've seen out there is because that valve there, people build a home or live in a home, and like all valves, they have to be exercised. And if this valve is not exercised, it won't work when it's needed. So say there's an emergency inside this house and I have to turn the water on, and this valve hasn't been operated in 20 years. And so what happens is that when the operator tries to close that valve, the rubber parts or even the metal parts inside don't work properly, and it does not close. And then you hope that you can put a key in here and operate this curb stop valve here. Again, valves have to be exercised, and that doesn't matter if it's the little ones inside your house or the big ones out there in the road. If you're not putting a key or turning them once in a while, or that's not part of your maintenance program, then you can get yourselves into a lot of trouble. I've had operators go out on a water main break and they try to close the valves, and they can't because they've been not operated for a number of years. So you can see what would happen. Then they would have to go and shut off another block of town and another block of town until they can find where they can actually shut these valves off, or the valves are in a proper condition to be used as a shut-off valve. So always keep that in mind. Exercise your valves, whether that's inside your plant or outside in the distribution network. We also have something called electrical or pneumatically operated valves. And electrically, that takes a signal from maybe your computer system and it will operate the valve. Usually it's for remote control action. A lot of the newer plants have this, right? I type in my computer, I need this valve to open, or it takes a signal from your PLC or your program from your SCADA, and it will tell the valve to open a certain way. Valves can be used in this example, in these pictures here. You can see these two here are pneumatically or air operated valves. It sends a signal, and an air supply is on the top of the driver here, and it will open and close the disc. These two particular valves are two butterfly valves. The blue one there on the right, you can see that the disc is white and the seat is black. And then on the one in the gray on the left, looks like the disc is silver and the seat is white. Now, when I talk about disc and seat, these are really, really important. That's the most important part of the valve. And on the side of every valve, it's listed the type of material that those seats and those discs are made of. So they have to be made of a material that's going to be compatible with what you're pumping. So if that's chemical, it better be compatible. That rubber or that seat part better be a material that will withstand that. And the same thing with the disc. You don't want a disc made of a metal property that's going to corrode prematurely because you're using a chemical. So always think about that. Also, there's automatic operated valves, and these respond automatically to some sort of pressure in your system. Really common ones in the distribution and even in the plants are the pressure release valves or the PRVs. There's also the check valves too, right? They automatically work. Air release valves are what they have is altitude valves. And we talked a little bit about altitude valves in our lesson last week. PRV is a big one though. Excuse me. Here's two examples of PRVs. The one on the left here, that little silver one, or the gold one here, that is usually what you find inside a house. It will step down pressure. Say a pressure in a house, I find it's around between 30 and 70 PSI. And that's pretty typical for what house pressure is. Any lower than 30, things don't work properly. Any more than 70, and you can have potential damage out there. So the little gold guy is really just to protect your house, and that's it. Whereas the blue one on the right here, that might be stepping down main pressure. So if I have a water main and that pressure is starting to get really high in that water main, it will go through a PRV station. And inside that PRV station will be this blue valve. And this is just a big version of that little gold guy. And it will step down the pressure in the entire system instead of just one house. So this might step down pressure for a whole neighborhood. These things they work well if they're serviced all the time. You notice the copper lines on there, there's little strainers. These things have to be serviced. And the dirtier the water source, the more times this could potentially get plugged up. in those little copper lines there. So it's really important to keep these things clean, and if your water source isn't clean, or else you could run into a lot of trouble. And these are automatically operated valves. So let's talk a little bit about valve types, right? The ones we're going to talk about are the main ones: the gate valve, the globe valve, the butterfly valve. There's a ball and plug valve too, and they operate similar. We're going to take a look at how they operate and some of the pitfalls behind it. First, we're going to talk about here's a gate valve, and a gate valve is, you know, and you can see it's exactly like its name. In that red piece in the picture there, it goes down and blocks the flow. The one big thing here, and I'm going to get my pen out, and I'm going to use green so you can see it. So this is really good for two things. We talked about losses last time, and you can see how when that gate, that red part up here is open, flow just goes right through. It's unrestricted, and that's how it should be. When this thing is closed, it closes right in there, blocks the flow off. One of the biggest rookie mistakes that are done here is, say I have a water break, and I'm going to send you guys out to fix my water break. Water's pouring out the main, and I say, hey, you guys, go shut that valve. You go there and you put your key in, or you turn the wheel, and you're going to try to get this thing closed. Now, you can see right here with the green pen here, you can see how during normal operation, material could actually get lodged in this little hole here. And right, that's the kind of the seat where the gate falls into. And what happens is that, you know, if I just crank on this, it's not going to close properly because there's debris right here. And that's a big, big problem. This thing won't close properly. So a lot of newer operators, they just try to close it and they're trying to, you know, and sometimes they will break the shaft here, the screw part, because they're trying so hard to close this thing to make the water stop, and the water isn't stopping. What you have to do actually is, what I like to do is downstream, I like to open up a fire hydrant or something like that. Something that creates velocity. Because what I want to do is create the velocity inside the pipe to scour this clean first, then try to move the valve. So I'll try to get this down, you know, I maybe put it down to about this level right there. And then what I'll do is I will open up a valve downstream, or I'll open up a fire hydrant and start letting a lot of water out and start to scour that bottom of that pipe so that I can clean that little section out in order to make that valve close down. So always think about that. If you have valves in your system, like a gate valve, it will not close sometimes because debris get lodged into that little seat area. And so you have to basically flow that water. Sometimes you're lucky that the water break is downstream and it's created enough velocity to actually scour the pipe for you. But if not, the trick is to open up a fire hydrant or something that's nearby downstream in order to clear this little area so that you can see that this will seat really, really nice. And that's one of the tricks. These valves here are buried usually, and you can see in this particular brown one, it's coated with an epoxy, and it protects that valve from elements of the soil and making sure that it's going to be. So these can be buried in the ground. It's not a big problem. Also make sure, you can see that there's valves are held together with bolts, and making sure the bolts are a proper material. I've seen, and I've dug up personally, a lot of these type of valves, and the bolts are gone because the bolts have rusted away. The coated valve body is still there, and that's not an issue, but they put the wrong type of bolts in there. And if you're burying this, especially in soils that are hot or corrosive soils, you need to have at least a 304 stainless or a 316 stainless type bolt. in order to make sure that the bolts will still be there when you dig this thing up. If they're not that tight, then chances are the bolts will be gone. They'll be corroded away. And I've seen that more and more times. When I lift the dirt off, that whole top of the valve comes off too, because nothing's holding it together but the dirt. Second type of valve we'll talk about is a globe valve. And the globe valve, you can always tell, because flow, you know, in the design, flow is going to come in, has to go up, and it's going to go out. So it's almost like it zigzags up, and you can see that on the design of the valve. So if I'm looking at that valve, I can see that it's going to zigzag up and down. This is very similar to how a typical compression hydrant works. It has a body, you know, and some sort of sealing device, and it's usually a rubber or some sort of rubber material, and it's just going to seat along a seating surface, and the driver goes up and down, and it just seats. Water has to change direction, so if I have a globe valve, there's going to be a lot more losses, because now the flow actually has to change direction. So there's going to be a loss as it's moving, and it's got to change direction twice. It's got to go up through that opening and down. And they're used quite a bit. You know, you always have to keep an eye on the seat and making sure that the rubber type material is not compromised. When we talk about fire hydrants, this is exactly how a fire hydrant works. It uses kind of a compression disc, and you're gonna put a seat, a compression disc onto a seat, and that's very, very similar to how a fire hydrant would work. And we'll see that in a few minutes. And that is called a globe valve. And that's how you know. If I look at a valve and I looked right through it, and if I can't see through it, the chances are it's probably one of these, because like I said, all you're going to see is a metal surface and a little passageway at the bottom of it. It's a good way to know that that's what that is. There's also a ball valve. Inside a plant, I see these a lot, especially the plastic style, the one on the left here. And it just basically has a plastic ball, or the one on the brass one that you see on the right here. It's just basically going to be, you know, when you turn it the one way, it seals like with a ball shape. And when you open it, the ball actually has a hole in it and water can go through. Again, it's another nice one that has very little losses, because the flow of water goes right through it. And there's nothing to really slow it down. For smaller applications, these are fantastic, especially in chemical additions and that kind of stuff. So I find that these work. Very, very common are the ones on the left here. I see these all the time. We have dozens and dozens of these on our chemical systems. Very cheap, very easy to use. But also, again, they have rubber parts on the inside. So always make sure that they're compatible with the product you're pumping. And for most of you, it's going to be chlorinated water. And chlorine really does a number on rubber parts. So making sure that the seats or everything inside these valves are a proper type of material. Let's talk a little bit about the butterfly valve. Now, the butterfly valve is the valve that's used for throttling. This is the only one I would really think that would be acceptable to throttle. Whether they're big or small, these are throttling type valves. One of the pitfalls here, though, is the black part here, the seat. And again, I've seen a lot of people order these type of valves, and it's the wrong type of material, especially in the chlorinated water. And what happens is that these black parts swell up if they're not compatible. So if these swell up and I try to close that silver disc here, it can't seal, because the black part, the seat, is deformed. And it's really, really hard. The other thing too, there is some losses, because the water does slow down because there's a disc in the middle of this, right? So you can't just look right through. So sometimes that's an issue. But it works pretty good. For cleaning though, that becomes a problem, right? So if I'm putting any sort of cleaning device down here, and we'll talk a little bit about that in a few minutes, something called a pig, and that's a cleaner that goes down inside a water main, and it will clean the inside. I can't get past there with these type of valves. It gets stuck. Typically, the rule of thought is a butterfly valve needs some sort of driver. And it's this black part here. It's not just a direct, put a key in and operate it. It needs some sort of driver, and you have to turn it a number of times. The other rule of thought with a butterfly valve is that it should not be buried. These valves are great for above ground or in a station, but not typically buried, and should not be typically buried. It's a rare thing, and it shouldn't happen. If it's in a chamber or something, that's great, but it really, these type of valves should not be buried at all. And just a note, and that might come up on your ABC test. And we talked a little bit about valves, again, have moving parts. They shouldn't seize. They have to be some sort of material. And so make sure that it's the right material. If it's going to be buried, make sure it's epoxy coated. Make sure it has the right type of bolts holding it together so that they don't corrode. Make sure the stuff inside, right? The rubber seats are a material, that's, going to be okay for the product you're pumping. Same thing with that disc material, right? There's all different materials. You don't want something that's going to corrode very quickly. You want these things to last, especially if we're going to bury these things. All right, let's talk now a little bit about some of the ones that we buried. We quickly talked about that corporation stop when you saw that. And again, just a reminder where that is, that's the one that's buried under the road here, right? So that's this guy right here. We'll talk about curb stop and corporation stop. And again, that does show up a fair bit on the test. What's a corporation stop? And it's a shut off at the main, but it's buried. Where a curb stop is usually accessible from grade, right? It comes, there's a box at the top, you can actually look in it, but a corporation stop is always something that is buried. Let's go back here. Again, those are the three big ones. A main stop or something is the one inside the house. So those are the big ones. Corporation stop, valve located at the street, at the water main, it shuts that water main off. It is buried, not accessible. Curb stop is accessible. It's a manually operated valve that's located between the water main and the customer's home. Usually that is the point of most utilities where the responsibility ends. And then they're usually that plug or ball style. And those brass ones I saw, those are usually a ball style. They have a little ball on the inside. And making sure too that sometimes that they're open correctly. If they're open a little bit, they're closed still, that the ball's not perfectly lined up, over time that ball is going to wear because water running past a valve that's not open properly is going to cause some issues. So making sure that that's always looked at. Let's switch gears into fire hydrants. And we saw fire hydrants a little bit when we talked about the flushing programs. And to me, fire hydrants do two big things. They provide protection for firefighting and they water main flushing. The one problem with fire hydrants is that they stick up everywhere, right? And sometimes, they get damaged quite quickly. It's a good way to allow large quantities of water through a system. It's fantastic for keeping your system fresh. The picture I'm going to show you, I actually took this picture and it was one of those days where, and you can see what our weather looks like. A fellow was coming down a hill in his automobile And again, in Canada, it can get very slippery in the morning sometimes. And unfortunately, he crashed into our hydrant. And we're going to talk a little bit about hydrants and the different types. Our hydrants have the valving below, and what they call the not a live hydrant, but it's going to have a dry barrel hydrant, which means that normally if I hit a hydrant, it just shears off and we don't get water flow. In this case here, this was an older hydrant and it took the compression disc right out of it. It was a bit of a mess. So there's a question on here, what could be the cause? On your SCADA, a pneumatic butterfly is showing closed, but when you look at the valve, it's open position. It was either set up incorrectly, which happens sometimes. They've got the open and closed backwards. There could be a failure of the valve too. But chances are if something's backwards, if you put a run command in or open command, it should do open. And if it's not doing that or it's doing the opposite, then it's probably set up incorrectly. So that's typical hydrants. And you can see our weather's fantastic with all the snow there. We learned to drive in the snow very, this is a daily event for us to drive like this. Like I said, there's two types of hydrants, right? We're really lucky because dry barrel hydrants have the operating valve located at the bottom, and that's done because we can't have that column inside the barrel full of water in Canada here, especially because it will freeze and damage the pipe network. So we have the stuff buried. In those movies, you know, when you see a car hit the fire hydrant and get the big geyser, that shouldn't happen. It did in this case, in this picture here, but chances are in a lot of new hydrants, there's what they call a breakaway flange, so that what happens when a hydrant gets hit, it just breaks off and falls to the side, but everything below is okay and no water comes up. It's just this particular hydrant was an old one, and the rod that goes to the bottom that operates the valve, it actually came out too when this thing was hit. And you can see this here in the picture. The one on the left, you can see how there's an operating stem, right? And so typically they will have a breakaway, you know, at the bottom here. So a breakaway flange would be here. This would be flush with the road, so that both the hydrant and the operating stem will break away in an accident. And that way it doesn't compromise any of this stuff here. This is the important stuff. Note here, see how there's a compression disc and it seals against a surface. That's very similar to that globe valve design. And that's exactly what these things are. In a wet barrel hydrant in the southern states and in warm climates, this is the type of hydrant that there is. Water is right up to the top. The barrel is completely, so if this hydrant was broken right here, all that water is going to have a geyser. It's going to escape. What kind of hydrants do you guys have? Do you have the wet barrel or do you have the dry barrel style hydrants out there? I would imagine you probably have more of the wet barrel style than the dry barrel that we have. Wet, yeah. That's more typical in warm climates. For us, because of freezing, we have to. And some of the real, you know, even these can be up to 12 feet deep where the valve. So that stem it goes down, you know, 8 to 10 feet down, just to protect it from freezing. And that's a real problem, right? You know, on a fire, and I have to use this in a fire situation, you don't want these things frozen because it doesn't work. And we still get a lot of frozen. That's a big thing, is unthawing frozen water mains and frozen hydrants. That happens all the time. So you can imagine a fire in Canada, and the fire department comes out and tries to hook up to a fire hydrant and it's frozen. And that could be quite disastrous for a homeowner whose home's on fire. Not good for the utility either. So we try really hard to keep these hydrants Some of the really cold climates, what they'll do is they'll fill this part, they'll fill this part here, the dry barrel part, they'll fill with a food grade antifreeze to keep everything moving or from freezing in some of the really, but again, to me, that presents sometimes some cross connection. Yes, it's food grade antifreeze, but if this valve down here isn't 100% serviced or sealing properly, then potential there is to have antifreeze seep into the water system, and that sometimes can be very dangerous. Talk a little about isolation valves. And again, the isolation valve is of choice, especially one that we buried, is going to be that gate valve that we talked about. The gate valve is the #1 isolation valve that's used out there. And it's going to be that gate style, right? And always remember, if you're going to deal with that, you have that little part at the bottom that you're going to have to scour in order for this gate valve, especially if it's been in service for a number of years. That's why it's also very, I can't tell you enough to exercise your valve. If you do not have a valve exercising program, you need to do that. It's like us, right? We need to exercise, else we're not going to work properly. Your valves are going to be the same thing. Shannon, you're right. Usually the pressure does, but what happens, say if there was a main break or something downstream, or lower pressure, it will, there's potential that you can have a negative pressure. So when we talked a couple of weeks ago about positive pressure in our system, that would prevent that. But there's a number of situations. If another fire hydrant was used nearby, that could cause a low pressure. If there was a main break in that area, yeah, it could cause a lower pressure and that antifreeze could get into the system. Typically, you're right though, the pressure would prevent that because the pressure should be greater on that side of the valve than where the antifreeze is. And that's pretty typical. And it's easy to get out, right? Once I open up that valve, that water will flush that antifreeze out of there. But there's a problem. It's like anything with cross connection. You don't know when potentially you can have a low pressure situation. And again, your two big ones are going to be a water main break, or somebody else is operating a fire hydrant nearby. So if that makes sense. We'll talk a little bit too about solenoid valve. A solenoid valve is a really small valve usually. It uses a signal from the PLC. Very similar to what we talked about with those pneumatic or electrical valves. This is just another type. Usually, they'll look something like this. They'll call ASCO valve. It's just a small valve that takes a signal and all it's doing is opening and closing. It's not toggling or modulating. It is an open and close. It's taking a signal and opening and closing. The signal from the SCADA is usually a 4 to 20 milliamp signal. And what it's doing, it's providing an open or close command. Typically, you see these, and they're just, this might open up a small water line or something, and that's typically what you see inside. A lot of your plants will have stuff like that. Little solenoid valves. It's usually just open and closed. We talked a little bit earlier about those pressure release valves, right? The little brass unit or that bigger blue unit. And they're used to protect your water system from excessive pressures, right? Excessive pressures, and when we start getting excessive, I'm saying pressures over 70 PSI. And as we start getting over 70 PSI, things start to happen. And that's not necessarily a good thing. So we have a pressure reducing valve. Basically what we have here is you got inlet pressure, right? And it might be, it has to move against a spring or another type of device. Sometimes it could be hydraulically connected, or you have something to lower and raise the pressure manually. Inlet pressure comes in, it has to basically work against the another diaphragm, and that diaphragm dictates how much that flow can leave and go to that downstream. So if I have 90 psi coming in here, and I open up this to make sure that maybe coming out of here, it'll be 60. And that's kind of what you want. It protects your system, right? And you can adjust this for what you need. If I want 70 or 80 over here or 30, it will adjust it to. I have a couple of really large PRV systems here. I have probably 120 psi coming in and 30 leaving. So it steps it down a fair bit, and that protects our customers downstream. And these are big, they're about 12 inch in diameter, the diaphragm. And those are some really big ones. But it does protect our system out there. All different styles. And again, once in a while, the diaphragm has to be serviced and the driver. This particular one here uses a manually operated handle to adjust it for pressure. You can have this adjusted for hooked pneumatically, so you have water pressure on the downstream side controlling the diaphragm. They can be usually dynamic, Shannon, so when I'm doing it, you want water flowing. So what I like to do when I set these up is have my minimum flow, and I'll set the pressure, but then I'll also go back and open it up. So what I like to do when I set these things up, typically, if I have a fire hydrant in the zone that is serviced by the PRV, I'll go and open up flow, because what you want to do is set these things through maximum pressure. So sometimes what I'll do is I'll get the staff to open up a fire hydrant and get that pressure and that dynamic situation going so that I can set that pressure at that point in time. So I look at it usually when it's static, but I like to set them up, you know, while things are flowing. And so that's really important, because the rubber hits the road when these things, you know, especially in a fire or a hydrant use situation. That's your worst case scenario. And you got to make sure that these things are working at that point in time. And that's typically how I set them up. Not everybody does that, but that's typically what I do. Check valves is also something you see, and a check valve really is a one-way valve, right? A responsive flow in one way through a pipeline. And some of our pumps and our chemical pumps, a foot valve is a type of check valve. Typically, we will see this style. It's a swing type, you know, and it's just on a hinge. Water has to come through. It opens the hinge, and that hinge, you know, when the water stops, water typically can't go backwards because there's a seat here, and this hinge stops the water from going backwards. You know, it works well. Typically at the exit or the discharge of a pump, you'll see a check valve. And there's all different styles of check valves. There's a ball check valve. There's this style here, which is your swing check, and it does all the same thing. We don't want flow to come back, you know, and I always look at that, you know, when water goes to my customer, I don't want it back. But typically on the discharge of a pump, you'll see it. You'll see a couple of things actually. In this next picture here, there we go. You can see this part right here is your check valve. So this is a vertical turbine pump, which we'll talk about in a few minutes. Water's going to come up, go through. We have an air release valve here, typically because it's one of the higher points in the system. And then it's going to go through a check valve and out to your system. And that's a pretty typical situation you'll see. You'll see a check valve and an air release valve on the discharge side of a pump. Okay, let's switch gears into water pipe itself. And again, we talked about the valves that control that, but the pipe itself is used to move water through a water treatment system and from source to tap. And again, there's some of the terminology, and sometimes it's different everywhere. Water pipes are used, are big, and they can be called trunk mains. They can be called transmission mains. They can be called arterial mains. They're all different sizes. Typically, the big giant ones are called trunk mains. And whereas this, as we're starting to get a little smaller, transmission mains, maybe even smaller, arterials, and then once it leaves the main and goes towards the house, and we call that a service. So water service is usually from the main to the house, and that's when we use those corporation stops or the curb stops. Usually under pressure, and they're buried underground. And again, more for protection, right? We want to make sure that they're protected from the pressure, but they're also protected too from contamination from the surface. So not always the case, right? We found that the hard way in some places here in Canada, that we can't actually bury pipes. We have to do something different. And I showed you last time that a lot of northern communities here in Canada have to use a truck. They'll fill a truck, and the truck has to be the pipe network. Other places have something called a utilidor, and I think I added a picture of a utilidor later in the presentation here. Again, pipes come in all different sizes, right? And it's definitely used to suit the specific application and your customer, right? How many customers do you have? Do you need fire protection? Is there industry? These are the things you're going to have to think about. They could be 1/2 inch to, huge mains. That's typical. They have to be sized enough though to make sure that you're got the demand covered. But remember, we talked about not just the demand, but there's friction, right? And this friction causes loss of energy. So we have to make sure that we have a pipe in there that's going to be able to provide the service for our customer. And that's service for drinking water, water for usage, whatever that may be, whether that's domestic or industrial, or in fire protection, right? You've got to size that, because if I have a huge building, I better make sure I have enough water to actually fight a fire in that. And those are the two biggest things you got to always think about. Lots of material pipes too, like all different types of material. This is really neat. The picture here, all different types of pipes have been used, right? Right from wood stave, cast iron, galvanized, AC or asbestos cement, and now typically it's going to be a plastic type or a PVC type. This particular main here is a wood stave pipe. You can see it here. It's basically, it looks like a hollowed out tree, and they put banding or some sort of banding or chains around it. I know in a neighboring community here, just 1/2 hour to the north of me, they're in their downtown core, they still have wood pipe, if you can believe that or not. Some of the old trucks, and when I first started in the industry, the operators would have wooden plugs in their truck so that they can repair these pipes. And I thought, wow, like who would have known that these pipes here were probably in there for 100 years are still in service. Typically, you don't see that. In communities, especially in the 50s, 60s, and 70s, the materials went from more ductile iron type pipe to I see a lot of cement style pipes, asbestos cement, and unfortunately asbestos is quite a nasty airborne contaminant now. So any repair of this type of pipe can cause you a lot of problems, and we find that here In the 1970s, a lot of the services and the bigger mains were made from asbestos cement. Very good pipe, but very dangerous to repair now because of the spores that are created when you cut into this pipe. What type of pipe is typical where you guys are? What do you guys are typically using for types of pipe? I'm curious. Is it more of a plastic type pipe, or do you get more of a iron type pipe? What type of pipe are you guys using? You can throw that in the chat function. I'm curious to see what you guys tend to use. You know, I've seen it all depending on where we're at with types of pipes. I've seen all different types of pipes. Typically, this is what we have now, right? Most new installations and most updated installations are made either from a PVC pipe, which is what you see here, what they call, you know, blue brute, they'll call this. That's pretty typical. Ductile is still quite popular. I like ductile iron pipe because it's easy to repair, but typically HDPE, PVC that is definitely the pipe to use. Services though, you know, typically here in the 60s, 70s, and 80s, and up until early 90s, typically here service lines were copper. And copper was significantly. Back before that, like if you had a house in the 50s, galvanized was very, very popular. And galvanized is one of the most awful things to deal with. Here, they're at the point where insurance-wise, if you have a galvanized line, it has to be removed because there's so much issues with galvanized services. People have moved more towards the copper, or you know, mostly now more into some sort of plastic or HDPE type service lines, and that's pretty typical. Again, just because they do stand up to a lot more pressure, it tends to work really well. Like I told you, I thought I'd show you this picture. This is a community in the northern Canada here. And you can see this is a utilidor. This is how people get their water. All the water services are done in these little heated, you know, so you can see this is the main, this is the service going to the house, right? And there's little, like, you know, this might be a PRV or a station in here. Operator will open the door, check the heat, right? This is how people get their water. It's all above ground. So there's these utilidors all through town. Typically, what they'll have is oil heated huts like that one there, and it will heat that whole structure inside, keep those pipes nice and warm. They'll have temperature sensors on the inside to make sure that this is all protected and warm and there's no freezing. And that's, you know, but typically they're buried, right? Sounds like yours is buried 4 feet. Mine's going to be buried 8 for frost protection or protection from freezing. And again, we want to make sure where pipes are not buried, in this case here, they are going to be protected somehow. This is called a utilidor. And this is, again, used quite a bit in northern Canada to convey your servicing or utilities. Inside here, you also have all the other pipes. Typically, there is no sewer pipes that will get trucked away with using trucks that will suck out a tank of inside each person's house. That's fairly typical. Just because of the cold climate, wastewater treatment is also quite a challenge. All right. Again, when you're looking at how pipes are buried, you're going to look at working pressures, right? That's going to be the big one. And we talked about making sure that the pressures are correct using your PRV valve. If the pressure is too high, you can damage that pipe. You're also going to look at corrosive soils, right? And typically, any soil that's close to, say, a river or a waterfront is typically probably corrosive, more corrosive than you know, and that's not always the case, but it's very typically. Or it had water at some point in its history. It was an old riverbed or that kind of stuff. Those type of areas have really corrosive soil. You're also going to look at other utilities and making sure that definitely that there's no issues with corrosion from that, or even sewer, right? So if you have a sewer main that's nearby, and if that sewer main is compromised, you got to make sure. Typically, water pipes are put in above the sewer line. So if there is a crack or a problem with a sewer line, it leaks below the water line, which should be above in an open trench. They should be surrounded by compacted sand and gravel and bedded properly, right, to make sure that they're protected for damage, and definitely after the construction as well. All right, before we go into water quality, let's take a 5-minute break. Ignatius, we'll take a 5-minute break.
Okay, 5-minute break, everyone.
Let's do part 2 of this. So thanks for paying attention this morning, everybody. I know it's early, and it's not as early as it is for me right now. It's my staff just got to work. It's 6 a.m. right now, and it's I just said good morning to my staff as they start their day here this morning. So let's talk a little bit about water quality out there. You know, one of the big things with the system, you know, we treat our water, we make it good, everything, you know, and then we get to a point where our water mains, you know, has a problem with bacteria, or it gets dirty and something. You know, my system here, what I really find is that because in the winter, I make maybe 10 million liters a day. And that's pretty a typical day. We have a lot of grass and whatnot. So what happens in the summertime, I can make up to 40 and 50 million liters. So that's a 4 times volume difference. And that's hard, right? So when I'm designing my system to have 40 or 50 million liters a day plus fire protection, and then now it's reduced to such a small amount, the water doesn't move fast. And it sometimes some of my dead ends get stagnant, and we have to deal with this. Old systems, the way they did it, and I'll take my pen here, is that they would run a main down, you know, and they would service this subdivision, and they'll service this subdivision, and they'll service this subdivision. And that's, you know, that's tough. If there's only, say, one house over here, then there's all this volume of water in this water main that, you know, gets stagnant. And a correct way to do it is that they should have looped the system together and made a grid so that the water can move around wherever it needs to move, and not just a dead-end main. Unfortunately, in some of the designs that were done at the time, especially in the 60s and 70s, that's not the way it was. And because we can't have this system looping, or it wasn't available, we need to go out there and flush and make sure that that's, you know, nice and safe. We've all seen this type of thing here, right? We open up that fire hydrant and look at that orange or this really ugly mess that comes out of there. And that's really typical. And, you know, especially with ductile iron pipe. You have a lot of ductile iron pipes, and it looks like you guys have a lot of DI pipe by looking at what your comments back. If you're not flushing from time to time, this is what's going to happen. So you can imagine, yeah, that dead end main, but say if there was a water break or something and the water moved from this location into the drinking water system, and that's going to go into your customer's pipes, and they'll be drinking this stuff. And imagine getting a cup of water that looks like what's coming out of this fire hydrant, and that is not a good thing. So you have to really think about that. So big maintenance duties are going to be water main flushing, equipment exercising, and again, we talked about the valve exercise. And valves, A hydrant's a valve, so you should be that. Leak detection, repairs, and upgrading. These are the things you got to be thinking about in your system. Leak detection, I mean, that's fairly new, and water loss has become a big topic as well as leak detection. Now, if I can find and fix a leak before it surfaces, it prevents a lot of damage. And if I can prevent damage, that prevents a lot of cost. So it makes a lot of sense to make sure, especially if you have soils. A lot of soils we have here are silt and clay. And what happens when silt and clay gets wet, it liquefies and it can do a lot of damage very quickly. So really your maintenance program is going to be number one in making sure that you're preventing any sort of future issues. But at least valve exercising and flushing, those are two really easy things that you can do. And we'll talk a little bit about that in a bit. Again, upgrading things, right? This is my crew actually right here. They're actually installing a new plastic PVC water main. And they're using what they have here is a thrust block at a 45-degree angle bend. And all my bends, I have thrust blocks like that to prevent any sort of pipe moving. Our pipe moves for two reasons. A lot of times in a case of pressure, right, you get that water hammer and pipes will move a little bit. For us, it's frost. The frost will actually move those pipes a fair bit. So I usually have to make sure they're fastened to this particular block here so that they don't move around. And that's a big problem here. If I have a day that it's very, very cold into the minuses, so I'll say a minus 20 day, and then it warms up to 0, and then it becomes a, you know, that's a 20-degree difference. And if my frost moves around, my pipes will move around. And I tend to get a lot of water breaks because the strain on the pipe during the temperature change sometimes causes some issues. So I see that quite often. You know, depending on your water source, it contains debris that enters and accumulates in the bottom of the pipe, right? Depending on how your treatment. If you got really clean water, then your system's going to be really clean. If you have water that, say, it's really aggressive, it's going to cause issues in your ductile iron pipe. If you have water that has a lot of hardness, it's going to create scaling inside your pipe. So it all depends on your type of water quality that comes out of your treatment facility. Water main flushing moves water at high rate or high velocity and through that pipe network. And the whole idea is to discharge this debris or contaminants right out of there, or bacteria. Sometimes alone, though, that doesn't work. And so what you need to do is have put something inside the main to clean it, to clean the exterior or the interior of that pipe. What they're going to use is something called a pig. And you can see, now these aren't really common because, you know, you need a special pig launcher. They'll put this, it looks like those foam earplugs that you put in your ears. And you put that in the pipe itself. And then the water pressure will push this pig through the system and it will scour the inside of that main, especially ductile iron. Now, the problem is, though, if there's any imperfections in that pipe, and that pig can't get moving any farther, I'm going to have to take my tractor out to dig up this pipe and retrieve this pig. So I'll always have to be aware of that. Some of the newer technologies with this is that they use a slush. They'll use ice, and they will pump, you know, have a machine that makes an ice mixture, and they pump that ice mixture into a hydrant. They take the guts out of the fire hydrant, they put the ice mixture, they pump it through the hydrant one, and then it comes out the next hydrant. And inside, as that ice mixture is moving inside that pipe, it will scour a little bit that inside of that pipe. It doesn't do as good a job as a pig, but it definitely does do a better job than just flushing alone. And that is called pigging. All distribution systems are unique, and again, depending on the type of material you're using, the type of water, but you should be flushing annually. You should. And again, depending on the type of system you have, there might be more or less flushing that's required. You should also think too, if there's special events that happen, if there's contamination, you should go and flush. If there was a water break in that area, you should flush. If there was a repair of the system in that area, you should also flush. These are areas, things that you need to do. Even new installations, you should flush. So making sure that flushing is done, because if it isn't, sometimes contaminants can sit in the main and it can gather in some of those dead end locations. And that's not what you want. You want to make sure that you're dealing with this. Hydrants are what's used, right? We're using hydrants to discharge this water. Why hydrants? Because they got a big volume of, that's how you move these big volumes of water. Hydrants usually has a 4 to 6 inch main. That's what these things are. And that can move a lot of water. And that's what you want. We also use something called unidirectional flushing. And it's a method to use to flush water through the distribution system from one end to the other. Basically, what you're going to do is kind of systematically move all the water through one pipe instead of having water go through a grid. And there's a picture here. Where's my pen? So basically, in conventional flushing, I have water coming from a tank. It's going to be moving all directions through this hydrant. So it could be coming from this way. It could be coming from this way. It's coming from all over the place. So you're getting some water, but you're not, And you can see here, at letter F on the top here, it did a good job, but it didn't do a great job. If I do what's something called UDF or unidirectional flushing, is that I close the valve so that all the water and all the velocity comes through one way, and I'll flush everything one way. And then I will close that valve, this valve here, and open this one and do the same thing through here, right? So what you're doing is you're basically creating more velocity, more power to flush the main. Instead of just opening a hydrant and letting the water come from all over the place. You're controlling where the water's coming from and where it's going. So that's really important. Unidirectional flushing, that's becoming more and more popular. Here's two of my hydrant personnel. You can see here, yeah, we do deal with a lot of snow, and these guys are servicing and exercising this particular hydrant. One thing to really note here in this particular instance, every time the fire hydrant is used, in this case, there was a small fire in this neighborhood, and that the fire department used this hydrant. It needs to be checked and flushed, or checked after use to make sure that there's no debris, because you flushed a lot of stuff through there. And after you've flushed a lot of things through a hydrant, it should always be triple checked to make sure. So I always get my guys to go in, they take it apart, they do an inspection, and then it's deemed back in service. So these guys are out there doing some work on this hydrant today. When we talk about flushing velocity, an operator should develop some sort of operating procedure and how to flush it. It's also really important to let your public know, because if you're moving that colored water through your system and they just happen to be doing laundry, you can stain people's laundry, people can turn, maybe they're having a bath, something. You should let them know that you're flushing, that there could be some colored water. And that's only, it's always good to let them know what's going on. Again, they should be done at night. And it's not always easy because staff usually aren't working. And the big thing here is 1 meters per second. You have to develop a velocity 1 meter a second or greater in order to make this work. So it's super important. Don't do it during cold weather. I had a hydrant mechanic. He did some flushing on a hill, and he blew the water onto the road, and the road iced up, and a couple of cars came over the hill and caused a fairly significant car pileup, an accident, because of the water that froze onto the road. So always be aware, you know, and again, not necessarily for you guys because it's nice and warm where you are, but here we have to be really aware of where we put that water. The other thing that's not thought about a lot either is that because the water that comes out of a hydrant is chlorinated, that you need to think about dechlorinating that water using some sort of product, using a sodium thiosulfate or a vitamin C, something to dechlorinate, right? And vitamin C is becoming more and more the industry standard for dechlorination of anything. You know, when you go to a public restaurant and you get a glass of water and it has a lemon in it, the lemon is actually used to dechlorinate that water. And that's what it's for. We do it here. I have a dechlorination room that has vitamin C in it, and that's what it is. We use it to dechlorinate that water. Another big thing, and it's fairly new, and people are starting to get on the program, is water loss. And part of water loss is leak detection. And it could be a number of things. Leaky pipes, you know, water main flushing. We have to figure out, we spend a lot of money on chemicals and people and our plants to make sure that the water stays in the pipes, gets to our customers. But if pipes are leaking, we should fix that, right? Because that's loss of revenue. Plus two, it could potentially cause damage to our customers' properties, right? In a water break or something's happening. So leak detection is used a fair bit. The other big one too is leaking pipes, you know, could allow contamination. And again, only when the pressure has been lowered. So if I have a main break in that area and there's some leaky pipes in that area, there's potential that I can have contaminants enter the system. None of us want that. That's really important. For instance, in this case here, if a pipe was drained, contaminated groundwater can enter through a crack, cause problems. It can sit in there. You don't want that. This is why two things. We chlorinate that water, and that protects us from potential issues. Also, too, there's potential operational health issues if you do not maintain the positive pressure. So it has to be maintained. I cannot stress that enough. Positive pressure has to be maintained the best we can, or else they can create issues. The other thing that's usually not thought of, right? And you know, I'll show you a picture of my staff. They're putting some new pipes in, but any new pipes and fittings need to be chlorinated or disinfected. So I always had bleach and mops, and so that the inside surfaces or the surfaces that the water would touch when I put the pipes together would have a disinfection to it. In this case here, you can see my staff here are putting in some new water mains, and you can see there's some valves, right? These are the gate valves that we talked about. There's the hex key at the top that you would put your key on there. My staff are putting these in, and you can see the material here. This is actually a really neat picture because it has a number of different materials. You can see, where's my drawing? By this guy right here, that's an AC pipe, an asbestos cement pipe. It's connected to a ductile iron T. You got a gate valve here, a gate valve here, and this is a new PVC line. You can see, right? There's another water line that's sitting in here, so this is quite difficult. I like what they've done here because what they've ended up doing is they also put bags over the end to prevent contamination coming in here. So they would swab or make sure that there's chlorination inside the valve and the new, you know, the T that they put in, right? Making sure that they maintain positive pressure. This would have been where the water would come in and services the new installation here. But you have to be aware there's a bunch of different water lines and other pipes in this particular trench. So difficult to use sometimes. And you can see, you can imagine this is a long way down in this particular installation. They definitely have to have their work cut out for them because of how deep the pipe network has to be. The other thing too is hydrostatic testing. And basically, we want to make sure that once a section of pipe, like the ones that the guys just put in there, we have to test it. So they'll block off one end, they will pump it full of either water, or they'll pump it full of air and see if that pipe holds pressure to make sure that it's safe or that the connection is correct. They will also chlorinate that pipe. Sometimes what they'll do is they'll put a puck of granular hypochlorite inside the main. And when they fill with water, they superchlorinate it at that time to kind of make sure that there's no contamination inside that pipe. Okay, last little part for today, we're going to talk a little bit about pumps. And pumps used in water treatment are designed to draw water from our well or our water system, and it's going to get it to our treatment plant. And then basically when the treatment's done, we got to take it from our plant and we got to get it out into those pipe networks. And so pumps are used typically. We also will use pumps to move product around inside, whether that's waste product in the form of sludge, or we can also have chemicals delivered to our processes via a pump. This is one of my old pump stations. These are 600 horsepower vertical turbine pumps, and they provided service from my clear well. And we talked about clear wells last week, and the clear well, and this would take it into the distribution system. Each pump has a unique operating design, right? Depending on what it's needed. And there's a bunch of different components involved in pumps. And so we have to make sure we choose the one that's going to work the best for us. Again, pumps can be self-priming, or we'll have to prime them, and we'll talk about why we have to prime a pump. Some are made to give us lots of pressure, and some are made to give us lots of flow. And so we got to make sure we choose the right pump that's going to do what's required. The two big ones we're going to talk about are going to be the centrifugal pump design and the positive displacement pump design. And those are the two big ones you guys are going to be working with. There's all different parts and pieces to each of these types of pumps, but these are the two big ones that you're going to be: centrifugal or positive displacement, or PD. Again, centrifugal pumps are probably used the most. This uses, doesn't build a lot of pressure, but they do move a lot of water. This is a vertical turbine centrifugal pump you see here, right? It's, again, like I told you, every time at the discharge end of this pump, there's your check valve and away it goes. Underneath a vertical turbine pump is always a clear well or some sort of water reservoir, right? So water is going to move up inside here and off it goes, right? So when you see this style of pump, the vertical turbine, it means that it's over a clear well or over a body of some sort of water. And again, it's centrifugal. Centrifugal pumps are a type of pump that applies principles of centrifugal force, right? And this is, I took a long time for me to figure out how this works, but it's really, really interesting, is that as your impeller rotates, right, water is going to come from the center of this pump here, right? So water is going to come in, and it's going to get thrown out, because it's like a merry-go-round, right? So if I'm looking at this, water's going to come in the center, and because that thing is moving, the water's going to get pushed by gravity to the other end. One of the big things I ask new students is that if I put this, there's no water inside here right now, and I put this into a bucket of water right now, and I turn this on, will this pull water up inside it if this was empty? And the answer is no, it never will. The impeller here does not move the water. And that's the biggest thing I want you guys to get your head around, is that the impeller itself does not move water. When water gets entered into this chamber and this impeller moves, the water is going to move to the outer edge. the action of the water or the vacuum that's created, that the water moving, the water creates the vacuum. So that vacuum pulls more water up to here. So it's the action of the water moving, not the impeller moving. So if there's no water inside here, it will never pull more water into that pump. So that's what they mean by priming a pump. You have to have water inside of this impeller body in order for this thing to work. No water, no more water is going to come. So you have to always make sure that there's water inside this. And a lot of times that's why they put a foot valve to hold water inside here. So when you start that pump, it's just going to keep going, because it's the action of the water moving from the center to the outside that creates the vacuum that pulls more water into the center. And that's how it works. The faster that impeller moves, the faster the water is going to move from the center to the outside, creating more vacuum. So if you can think about it, that centrifugal pump is more like a vacuum pump. The vacuum's created by the water moving from the middle to the outside. And that's how a centrifugal pump works. And that is why we have to prime these pumps. Because if there's no water, these things aren't going to work. Here's some different styles of pumps. These are coming from my some of my plants that I've had here. And this particular one in this corner here, this is your typical horizontal one, right? You can see here's your pump, your impeller's inside here. Water is going to get drawn into the center and off it goes. This is a vertical turbine here. Normally, we're only going to see this part sticking above the floor. This part's going to be in water, so I have to actually lift this pump out. I was doing service on this pump, and my last slide today, you can see my mechanics are actually putting that pump back in. The pump itself is actually down here. You can see the pump bowls. So this has got 1, 2, 3, 4 stages of pumps. Every stage of this pump provides more lift. So the more of those little balls that you see, the more lift you can get, right? And that's always a question, right? A pump in series and a pump in parallel. So a pump in series, which is what this is. So the discharge of one pump goes to the inlet of the second one, and that's in series, creates more lift. If I had pumps in parallel, like 2 pumps, it's going to give me more flow. And that's a question that I see comes up. So pumps in parallel create more flow. Pumps in series create more lift. Okay, let's talk about the impeller. And again, as the water enters the impeller, it's thrown by the rotation of the impeller, right? It's thrown to the outside. It's just like a merry-go-round when you're kids, right? You know, you get on this merry-go-round and your buddy's spinning around, and what happens? Your body wants to fall off the merry-go-round if you're not holding on. It's the same thing inside that pump. That's exactly what's happening. The velocity of the water on the outside of the casing depends on the speed of the impeller. Faster the impeller is moving, the faster that water is going to move from the center to the outside. And that's the impeller. All this, the fancy word for it it applies something called Boyle's law. And Boyle's law basically, the accelerated water flow creates a low pressure zone at the middle of that impeller. It draws water back into that pump. That's what happens. Velocity creates a low pressure zone. And that low pressure is a vacuum is enough to pull more water into that pump. And that's using the properties of Boyle's law. Let's talk a little bit about some of the pump parts here. And the rotating impeller, we talked about that. It sits in something called a volute, and that's usually that snail shell looking thing that you see here. A diffuser is similar to an impeller, but the blades are angled. So that's the difference between a regular impeller or what they call a diffuser, is that the vanes are angled a little bit more. This is just a a volute here without an impeller, and you can see that here. You know, here's looking at it through another, and there's your eye of your impeller. That's where the water would come in. And again, you can see how these vanes are quite angled, right? Again, capacity is always affected by the size of the motor and the type of diffuser or volute that you have here. The type of pump is usually best suited for moving water in high volumes. Doesn't make a lot of pressure. One of the questions you get here, because it doesn't create pressure, it's okay to start this pump with the discharge valve closed. It will not do any damage because it does not create pressure, right? So that's something really important, because the positive displacement pumps that we'll talk about next definitely does. So here's looking at a couple of different styles. This is called a horizontal split case pump, right? It's not a vertical turbine. Basically, the impeller is inside here. You can kind of see the outline of that in there. It sits on a shaft that comes across, and water just moves. Sometimes you see these in inline booster systems, and it's really typical, but it's called a horizontal split casing pump, and it's a centrifugal style. Typical, like you saw the one in that other picture, as a typical centrifugal pump design. This is vertical turbine, and a vertical turbine just takes into place a number of different stages. So this one has 1, 2, 3, 4, 5 stages. So water's going to come in, spin around, go to the next one, spin around, next one, spin around. So this one goes through 5 stages, and it creates more lift to get that water moving from the bottom of the clear well down here and out the discharge. Usually this is the floor, right? And we don't see this part. This is under the water in here. And that's called a vertical turbine centrifugal pump. Let's move for positive displacement. Now, there's a number of different positive displacement pumps that are used for, usually what we see here is positive displacements used for chemical delivery nowadays. Basically, here's a type here. This one's called a peristaltic pump, and it's a type of positive displacement pump. It's got a tube, and basically you got rollers. The roller will move, you know, and squeeze that tube, and that you can see between this roller and this roller, that section of fluid is getting moved out the discharge. And because that it's creating a vacuum, it's causing lift to pull chemical in and push chemical out. And that is, now this will create pressure. So if you shut the valve here, this will continue to make pressure, and it will go boom. It will explode. Something will break, whether that's the pipe or the tube inside here, but something will break. So it's really important, never ever close a discharge valve on a positive displacement pump, because it will build a lot of pressure, and that will cause a lot of problems. Here's some bigger style, same thing, hose pump or a peristaltic pump, and these are just a bigger version. This particular one was pumping hypochlorite or hypochlorite solution. We also have the diaphragm pump, and before the peristaltic pumps were really popular, people used the positive displacement pump, a diaphragm style, and basically it had a diaphragm on the inside, and it was used mostly, and this is the LMI version. You see a lot of these styles still out there, and it used, it would suck the water in with one stroke, the valves would turn, and would push the product out on the upstroke. So downstroke, it would pull product in, upstroke, it would push product out. And that's your typical diaphragm style pump. This was really, really popular. A problem with this is pumping hypochlorite. It would airlock a lot, especially with hypochlorite solutions, and it became very problematic. And a lot of these were replaced with that hose style or the peristaltic pumps later in life. Before we get too far, I'm going to show you a quick movie. So just bear with me here for 2 seconds. Okay.
Yeah.
And just putting a movie on here.
Okay.
Go. Okay, can you guys see that screen there? It should have a roller and a tube. This is actually one of my movies there for my plant. I'm just gonna share the sound here. Hang on, so you guys can hear what's going on. Okay.
Here's a peristaltic roller and hose. As you can see here, we got a nice hose. It's got to be made of a rubber or some type of material that's corresponding to the material being pumped. In this case, is our hypochlorite.
So we'll take another look. So basically, and that's what we have here. Let's go back here a little bit.
Peristaltic roller.
So there's a roller and tube. So basically, I'm going to put that tube in. And one great thing about these things is that the product never ever touches the roller or the pump mechanism, right? That stuff stays in the tube. And so you can pump some pretty awful things without ever touching that particular device. Okay, I'm going to show you one in use here. I think I'm going to use, I think I have one right here. Let's bring this video up here.
Next room we're going to see is the coagulant aid room. And what does coagulant aid actually do? So this, if our regular coagulant isn't doing enough, what this can do is give us a little bit more charge when we need it. So if we have to get more color removal, this is what we're going to do. Again, we're using a pump skid, peristaltic pump like we saw earlier. It's turning really slow.
So you can see it here. This is pumping chemical in this case here. A couple of things we learned of today, we see in this video here. You can see our ball valves are being used, typical ball valves for chemical use. You can see the peristaltic pump. Again, it's pumping chemical in this case here through this peristaltic pump system. Works really, really well, and away it goes. Again, the pumps, the maintenance for here is that we take the roller out, make sure the roller is greased properly at periodic times, and that the hose once in a while is also replaced. So it works quite well. These have replaced those yellow pumps that we talked about, the diaphragm pumps, and they're used more and more and more. I use these for all different purposes. It works really well. I'm gonna switch gears to another video that shows I have some older diaphragm style pumps that I also use. So let's go take a quick look at those while we're here.
Next room we're going to see is the coagulant room. This is the plant's made coagulant. And we talked earlier about what coagulant does. It's our liquid positive charge. We also have a nice big large tank here. It's a little over 30,000 liters. Product gets trucked in. You see the pink hoses goes to the top, drops inside. And what we're going to do is we're going to pump this stuff. Now, tanks like this need to be accessed from time to time, and you can see here access points at this point. Product's going to leave through this network here and into 2 diaphragm style pumps.
And you can see here, these are older diaphragm style pumps. You know, these were used quite a bit. This is just a bigger version. Again, a diaphragm pulls in, it'll pull that product through that pump. And then as the diaphragm comes back, it will push the product through and off it goes. And these are really well used pumps before we went to the peristaltic style. So, okay, I'm just gonna go back to the presentation here, so bear with me. All right, you should see the diaphragm pump again. Give me a thumbs up if you can see that. Awesome, thank you. So those are the positive displacement pumps, and those are a couple of different styles. Let's put the chat thing back on here. Yeah, typical, you know, like nothing wrong with the diaphragm type pumps. And Dwayne, I see that you guys still use them, but we have moved towards more peristaltics. I guess cost is easier, easier of use to cleaning, and you know, still widely used. But I think you're going to see more and more people are going to move towards more peristaltic. As we get moving further into some more solids removal or sludges and stuff, we use something called a progressive cavity pump. And this is also called a moino pump. And it has a screw on the inside, an eccentric screw. And it moves fluids that are really viscous or really thick or sludges and stuff. And you see these in a lot of plants that move sludge. We use this for our basically our sludge coming off our dissolved air flotation, and that we move that product here. It's more like a oatmeal consistency, and we tend to use that with these style of pumps. It works really, really well, but at some points, you know, a typical centrifugal or even these smaller peristaltic pumps would be able to actually move that viscous product or that thick product. You have to go to something like this. Creates an incredible amount of pressure. So be very, very careful when you use these. If a valve plugs up or a valve is closed, it will actually explode the pipe. It creates that much pressure. So making sure that there is relief or pressure relief built into these, it's super important. These are 2 pumps that we had. I had an operator, again, shut the discharge valve on this particular pump you see here, and actually blew all the Schedule 80 pipe. And Schedule 80 pipe, for those of you who've used it, Schedule 80 PVC, it destroyed it. It broke it into little pieces, like in a matter of seconds. So be very, very careful in a moino pump or any positive displacement pump that you're not running it with the valve closed. That's fine for a centrifugal pump, but a positive displacement pump definitely is not something that I'm happy with. And we'll end with this slide here, and these are my mechanics putting in one of those vertical turbine pumps, and that was the one you saw hanging on the crane earlier. So you can see here that they're going to put that basket on the end to prevent anything going in there. This is a freshly rebuilt pump. You can see one of the stage or two of the stages. This is a 4-stage pump, and they're going to put it into the hole and button it back up. You can see the one in the foreground there, and that's what it will look like once it's actually put back into the hole. But that's typical what it is. It's a pump that sits in the water itself, and it works really well. So that is lesson 9, everybody. I appreciate the lesson today. Hopefully you guys learned a little bit about pumps and valves today. And we will see you back here next week for lesson number 10.
Right. Thank you very much, Mike. And would like to wish you a very wonderful day and wish all the team a wonderful day, and see you at the next session at 3 p.m. Those of you doing water distribution with Mike Epen, and at 5 p.m. our Wednesday webinar series. Goodbye. Have a wonderful day.
Thank you.